Hello everyone, myself G.Mohanavel, working as an assistant professor in the Department of Electronics and Communication Engineering in VSB Engineering College, KARUR. So in this video, we are going to learn some basic concepts in the topic of digital logic circuits. These are all the topics we are going to discuss in this video. The first one is, so what is meant by analog and what is meant by digital. Second one is basics of digital circuits. Third one, what is meant by logic gates. Next one is, what is meant by combinational and sequential circuits. And what is meant by half adder, half subtractor, full adder and then full subtractor. So these are all the topics we are going to discuss in this video session. First, if we start with analog and digital, first of all, we have to clear about what is meant by analog and what is meant by digital signal. See, if we take analog signal, so it is a type of signal whose characteristics is simultaneously changes with respect to time. Here the definition is, here the statement is given as analog signals are transmitted as a waves, the digital signals are transmitted as ones and zeros. So it is a basic difference between analog signal and the digital signal. So if you are processing analog signal, the signal will be processed as it is. We are not going to convert any analog signal into digital signals. When you go with digital signal, so whatever may be the information at the input side, so all those information has to be converted into binary values. We are calling that as digital values. The values are zeros and ones. Here the 0 represents off state, 1 represents on state. If we compare analog and digital, so which one is better in the sense, if you take analog signal, the accuracy is somewhat low and also it is affected by noise. When you go with digital signal, so it is represented with zeros and ones, so it is less affected by noise and also gives more accuracy. So it is a basic difference between analog and the digital signals. Okay, next if you take digital circuits. So what is meant by digital circuits? So it is here logic circuits that carries out some logical operations. To perform the logical operations, so what are the basic elements needed? The first element is logic gate. So from that name itself we can explain what is meant by logic gate in the sense, actually gate is a controlling element that operates based on certain logic. See, some of the logic gates are OR gate, AND gate, NOR gate, AND, XOR and then XNOR gate. So among these gates, two gates are called as universal gates. One is NAND gate, another one is NOR gate. So everyone knows this. So what is the reason behind that universal gates is, by using these two gates we can perform any kind of logical operations. We can perform OR gate operation, AND gate operation, etc. All the gates operations can be performed by using these two gates. That's why it is called as universal gates. Okay, this slide explains various types of logic gates and its corresponding operations. So first if we start with AND gate, so it is a symbol of the AND gate. This gate comprises of two inputs. So at the input we have to provide digital values. Okay. So what are may be the circuits? First we have to look at how many inputs are there. By using the inputs, you have to consider what are the possible combinations of input we can provide. For example, if a digital circuit consists of only one input, so we can provide two possible combinations of input, one is 0, another one is 1. So this can be identified by using the formula 2 power n. That n represents how many inputs are there for the corresponding circuits. So in this AND gate, we are having two inputs which are labeled as A and B. So if you are substituting those two input into the formula 2 power n, you are getting 4 possible combinations. That 4 possible combinations starts from 0 to 3. You can see this table. So this is the operation table of the AND gate. We are calling this as truth table. Okay. So the input you have 2 variables A and B, and also you have 4 combinations, and also you have one output which is labeled as F. If you consider the first combination, that is A equal to 0, B equal to 0, what will happen if you are using AND gate in the sense? So it is a gate which is responsible for doing the operation of logical and in the sense it performs logical multiplication. First, if you consider that first combination 0, 0, if you are multiplying both the inputs, you are getting output as 0. Likewise, 0 multiplied with 1, result is 0. 1 is multiplied with 0, result is 0. The last combination is both the inputs are 1. If you are multiplying these two inputs, you are getting output as 1. So it is the operation of the AND gate. The second gate is OR gate. So it is a logical symbol for the OR gate. OR gate also consists of 2 inputs. So we can generate or we can provide 4 possible combinations of input, and also consists of only 1 output. So what is the operation of the OR gate is? So it is a gate that is responsible for logical addition. AND gate in the sense logical multiplication, OR gate in the sense logical addition. Just consider the first combination A equal to 0, B equal to 0. If you are adding both the inputs, your result will be almost equal to 0. And also consider the second combination 0 and then 1. If you are adding 0 plus 1, result is 1. The remaining combinations are the same. 1 plus 0 equal to 1, 1 plus 1 equal to 1. Next, if you take NOR gate, actually NOR gate is somewhat similar to the logical symbol of OR gate. What is the primary difference between OR gate and the NOR gate is? You can see at the symbol at the output side you are having one bubble that indicates a complement operation or NOR gate operation. So actually NOR gate can be formed by using OR gate and the NOR gate. This operation is just opposite to the operation of OR gate. You can see the table here. And the next one is exclusive OR gate. We are calling this as XOR gate. XOR gate symbol is this one. Here also we are having 2 inputs, 1 output. 2 input in the sense we are having 4 combinations, that is 0, 0, 0, 1, 1, 0, 1, 1. What is the operation of the XOR gate is? You have to consider this combination of inputs. When both the inputs are same, this gate produces logical 0 as output. When both the inputs are different, this gate produces logical 1 as output. So this operation is somewhat different from the previous gate. AND gate in the sense logical multiplication, OR gate in the sense logical addition, NOR gate in the sense it is just opposite operation of the OR gate. XOR gate in the sense whenever you are having the input is same, output equal to 0. Whenever you are having different inputs, the output equal to 1. Okay, next one is NAND gate. So as like NOR gate, the NAND gate operation is just opposite operation of the AND gate. You can see the table. You can compare the AND gate and then AND gate operation. If you look at the table, here it is 0001. Here it is 1110. It shows that the operation of AND gate is exact complement of the operation of the AND gate. So next one is exclusive OR gate. This operation is just opposite operation of the XOR gate. In XOR gate, when you are having the input as same, it produces logical 0. Here, XOR in the sense whenever you are having the same input, output equal to 1. Whenever you are having different input, output equal to 0. The last one is NOR gate. So everyone knows this. It consists of only one input, one output. In a digital circuits, one input is there. We can provide two possible combinations. One is 0, another one is 1. So it is a gate that produces the complement operation. That is, if you are giving 0 as input, it will produce 1 as output. 1 as input, 0 as output. So next one is, this is one important topic, combinational and then sequential circuits. So this is very much important. First we can consider the combinational circuits. So it is a circuit which is designed with of only logic gates. That means it takes the input, processes it and produces the output based on the condition or based on the logical operations. It does not need to store any previous data or future data, etc. So this combination circuits will not consist of any memory elements. If you go with the sequential circuits, so it is also just like a combination circuit, but the difference is here also you are designing the circuit with the help of logic gates. Along with the logic gates, you are using a memory element. So it is a fundamental difference between combination and then sequential circuits. See, if you are designing combination circuits, only logic gates are used. In case you are going to design sequential circuits, along with logic gates, memory elements can be used for storing the previous values. Okay. Some of the examples for combinational and then sequential circuits are combination circuits in the sense half adder, half subtractor, full adder, subtractor, parallel adder, parallel subtractor, etc. Sequential circuits in the sense counters, shift registers, etc. In case of sequential circuits, we are using a memory element which is called as flip-flops. In detail, we will see about combination circuits. First one is half adder. From the name itself, we can explain what is meant by half adder. It is a digital logic circuit or it is a combination circuit that is designed by using logic gates to perform logical addition of two inputs. So it is a truth table of the half adder circuit. It consists of two inputs, two outputs. The two inputs are labeled as AB, two outputs are labeled as sum and then carry. We know that in whatever may be the digital circuits, we have to look at how many number of inputs are there, so that we can give possible number of input combinations. So in this half adder, we are having two inputs, so that we can give four possible combinations. That combination of inputs starts from 0, 1, 2, 3. This 0 represents the starting number, that is 0, 0 represents 1, 0 represents 2, 1 represents 3. Sum and carry are the output. First we can consider the first combination. So it is a combination circuit that performs the logical addition of two inputs. We are adding two inputs, sum equal to 0, carry is also 0. You can consider the second and third combination, 0 plus 1 equal to 1, here 1 plus 1 equal to 1. In these first three combinations, there is no carry, so all the values are mentioned as 0. If you go to the last combination, 1, 1, we are adding 1 plus 1, your result is equal to 1, 0. That 0 is called as sum, remaining 1 is called as carry. Your next step, by using this truth table, we have to design the combination circuit, that is half adder circuit. How we can design in the sense, you have to focus on the output, that is sum and then carry. You have to find how many number of minterms are there. First we can consider the first column as sum. Here, how many ones are there and what is the corresponding number, that is called as minterm. Here, in your next slide, we have given the minterms for sum and with carry. For the sum it is 1, 2. For the carry, the minterms are 3. It is nothing but in our truth table where the 1 is present. In that sum, the 1 is present in the place of 2 and 3. Sorry, 1 and 2. In carry, the 1 is present in 3. So next one is, by using this method, we have to create the expression. How we can generate the expression in the sense, with the help of this table we can generate it. This is called as K-map. So it is a K-map representation of two variables, A and then B. You have to consider these two inputs and then you have to map the value as 0, 1. Here it is 0, 1. The first box is numbered as 0, second box is 1, here it is 2, here it is 3. Our midterm is 1 and 2, so you have to place 1 in the place of 1 and then 2. So and then your next step is you have to go with the grouping process. Here there is no pair combination, so you have to individually group it. And then you have to form the expression as A XOR B. Here it is A and then B. By using these two expressions, you have to create or design the diagram for half-adder circuit. For the sum, the expression is A XOR B. So we are using XOR gate. For the carry, your expression is A and then A and B. So you are using AND gate. So next, if you go with the half subtractor, from the name itself we can explain it is just like the operation of half adder, but what is the difference is, there we are performing addition of two inputs. Here, in case of half subtractor, we are performing subtraction of two inputs. So it is a truth table of the half subtractor. Half subtractor also consists of two inputs, two outputs. Two outputs are mentioned as difference and then borrow. We know that digital circuit, if a digital circuit consists of two inputs, we are having four possible combinations 0, 1, 2, 3. Then what is difference and what is borrow results? First you have to consider the first combination 0 and then 0. If you are doing the subtraction operation, your difference is also 0, there is no borrow here, so that is also 0. So next combination is 0 and then 1. 0 minus 1 is not possible, so we have to get 1 borrow, so automatically borrow will be 1. Here it is 10, 10 minus 1 is, result is 1. Your third combination is 1, 0, 1 minus 0 is 1, here there is no borrow, so it is 0. The last one is 1, 1. 1 minus 1 equal to 0. Here also there is no borrow, so it is 0. In your second combination alone, we are having one borrow because 0 minus 1 is not possible. So the input A, we have to get 1 borrow. So this 0 will become 1, 0. Now you have to perform the subtraction operation. Here it is 10, here it is 1. 10 minus 1. Your result difference is 1. Already the borrow is 1. Again the same process for difference and then borrow. You have to find the midterms, then you have to go with K-map, then you have to generate the expression. Your expression will be like this, that is A bar B plus A B bar. Borrow is A bar B. By using this, you are implementing that half subtractor. So it is a logical diagram or circuit diagram of the half subtractor. Your next combination circuit is full adder. It is same operation of half adder, but what is the restriction or drawback of half adder is? Half adder is limited only for 2 bits. Full adder can be used for addition of 3 bits. It is also a combination circuit that is designed by using logic gates. It is used to perform the logical addition of 3 bits. So it is a truth table of full adder circuit. It consists of 3 inputs, 2 outputs. We know that if your digital circuit consists of 3 inputs, your formula is 2 power n, 2 power 3 is equal to 8. So there are 8 possible combinations of input we can provide. Starts from 0 to 7. For each combination, your result is given here, sum and then corresponding carry. It is nothing but you have to add all the three inputs and then you have to mention the sum value of the carry value here. You can consider the first combination, all the inputs are 0, sum is 0, carry is 0. Second one is 0, 0, 1. We are adding that sum is equal to 1, carry equal to 0. You go with that fourth combination. 0 plus 1 is 0, 1 plus 1 equal to 10. Your sum is equal to 0, carry equal to 1. So likewise you have to perform the logical addition of three inputs. Then as usual the same process. You have to find the midterms for sum and then carry. Then you have to go with the K-map simplification for three variables. Then you have to generate the expression for sum and then carry. You have to draw the diagram. The last one is full subtractor. So it is the combination circuit that is used to subtract three inputs. It is also consists of three inputs, two output. So three input in the sense 8 possible combinations starts from 0 to 7. It performs the subtraction of three inputs. So it is a circuit diagram of full adder circuit. So in our next video, we will discuss about sequential circuits.